In the parallel circuit, each resistor is connected directly across the power supply. So there actually can be a bunch of independent currents. It can go from the positive through resistor 1 back to the power supply. Go from the positive through resistor 2 and back. Or through resistor 3. So we actually can treat each of them as totally separate branches. So we just have to use Ohm's law and PIV on both of them. So I'll do the calculation for the 190 ohm, then I'll cut, and you'll see that the other calculations are done as well. On the Flickr album, there'll be a picture of the completed worksheet after. So we've got V equals I times R. So in that case, the volts are 24. The amps are unknown. And the ohms is 190. So we'll just divide by 190. And we get a current of 24 divided by 190 is 0.126 amps. So that'll be our current through our first branch. I'll do the other calculations now, and we'll cut back. So you can see for a parallel circuit, we definitely do not have the same currents, because each of these branches has its own resistance. So the voltage will impress different currents. I'm now going to calculate the power of our 190 ohm resistor. Then I'll cut away and do the other two. So the power will just be our current in that branch of 0.126 times the 24 volts. So 0.126 times 24. .02 watts. All right, I'll do the other two without you having to watch. All right, so there's all our powers. I wanted to try one other thing. I wanted to figure out what the total current is in this branch, where all three of the smaller currents have to act. We could use Ohm's law to figure that out if we just knew the total resistance of the circuit. So let's get the total resistance of the circuit. It uses this equation, which is a little bit tricky looking, but I think we could do it with no trouble. It basically says that 1 over the total resistance is going to be 1 over 190 plus 1 over 830 plus 1 over 450. So it's a little bit complicated. The easiest way to do it is just to break it into its pieces. So, a better calculator. So 1 over RT is going to be 1 over 190. So 1 divided by 190, which is 0.00526. Okay, so let's add those up. 1 over RT is 0.00526 plus 0.00120 plus 0.00222. 0.00868. So now we just invert it. There's an inverse key on most scientific calculators, and that is 115.21. So that's our total resistance, 115.21 ohms. Notice it's less than any of our actual resistors. That's because there's more than one road open for current to travel, so you open more highways, traffic flows faster. Let's just use Ohm's law to figure out what the total current should have been. The voltage in this case was 24. The current is I. The resistance is 115.21 ohms. So we'll just divide both sides by that. And we get 0.208 amps. Well, how does that compare to these currents? Well, I'm just going to go ahead and add them up. Put a little plus sign there. So 0.126 plus 0.029 plus 0.0533. And I get 0.208, the total current, which kind of makes sense because the orange current, the purple current, the green current, they're present in this branch, all three of them, so we just add them together. It's equivalent to Kirchhoff's junction rule. If you're in a class, let's discuss that. So our data shows us that as we go through and add up all our currents, we get the total current. So that's parallel circuits.